Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 4, Electricity and Magnetism, with a focus on Inquiry Question 1, Electrostatics. We're going to be applying the interactions of charged particles with this formula here, which is also known as Coulomb's law. Now, you'll need to use this textbook reference if you want to do additional reading. Today we're going to be describing what Coulomb's law is by depicting particular force interactions of charged pairs and dipoles. And we're going to do some calculations to work out what the actual values would stand for when charged particles are exposed to the electric fields of other charged particles. Now, to recap what we talked about before, in the previous lesson we said that if a charged particle is exposed to an electric field, the electric field will exert a force onto the charge. How much force the charge experiences will depend on the charge itself and the strength of the electric field. If we're dealing with two parallel charged plates, then the electric field strength is dictated by the voltage that's placed into the charged plate and the distance of separation between them. So you might want to picture it as having two charged plates. The voltage is what we have here. So it's how much volt is across these two plates, and then obviously the distance of separation. What this formula will also say to you is that the electric field strength within these two parallel plates is uniform, so it's equal throughout. If you have a look at this charged particle here, so it's interacting with our electric field, you can see one thing. I want to point that out. We can see that there is a change in direction, so there is a change in direction of the charged particle. We also know that when we're talking about electric fields, it's always moving from positive to negative. So there's actually two particles we see in this animation. Particle 1, the one you just saw there, that is a positive charge. The reason why we know that is because it is being accelerated towards the negative plate, while as the second charge that we see later on, that's a negative charge because it's accelerating towards the positive plate. You can also see the overall shape of the particle is sort of parabolic. So that's what happens when charged particles interact with electric fields. Their motion kind of follows this parabolic motion with the field there. What we can also deduce is the fact that if there is a change in direction, remember, if there is a change in velocity, so if there's a change in the velocity over time, we also have an acceleration. So we also experience acceleration. Okay, so how do we work out how fast or how different is the acceleration of this charged particle when exposed to an electric field? Okay, so what I want you to imagine is, how do we firstly work out the acceleration of the charged particle? Well, we know that acceleration is given as force divided by mass. And force is given in newtons, mass is given in kilograms. Now obviously when we're dealing with charges, we're probably looking into protons and electrons. Now the mass of a proton and electron should be on your formula sheet, so that shouldn't be too difficult to find. So the question is, how do I know how much force is being applied onto my charged particle? Well, there's two formulas we can use. We know that the force exerted on a charged particle is Q times the electric field strength. We also know that the electric field strength, in this case here, if it's two charged plates, is given as the voltage divided by distance in separation. Okay. And so we can rearrange our equation to ensure that F is the subject. So if I sub that into my equation, I'll get the following. So the acceleration on a charged particle is equal to the electric field strength of the charged plates times the charge of the particle, so charge of the particle, times its mass. So it's these three variables that will affect the overall acceleration of the charged particle when it goes through an electric field. Another way we can also measure electric field strength, if you recall, is by measuring the density of the field lines. So if we have a greater density of field lines, we know that we have a strong electric field. Now, from last lesson, we mentioned if it's a point charge, the electric field is going to move in sort of a radial form. So it's going to go in all directions, and you can sort of draw a nice little circle around where everything is going. Okay, so we know that density is sort of, if we want to calculate the density, then we want to firstly work out how many electric field lines are we generating, and also how much territory is being covered. Okay, so if it's going in a sort of radial form or in a circular form, we know that the area of a circle is 4 pi r square. Okay, so if we want to substitute that in, we can say that the density of the electric fields is given by how many field lines we have. So number of electric field lines divided by the overall area. Obviously in calculations they don't really ask you about what's the overall density in this format. They will ask you to find the electric field strength, but not based on the density. And so we find a little relationship because we know that the density is related to the electric field strength. We can say that the overall intensity of the electric field, or the strength of the electric field, is inversely proportional with the radius squared. So inversely proportional to the square root of the radius, or the square of the radius, and it is directly proportional to the charge of the particle, so it's directly proportional there. So the stronger my charge is, the stronger the electric field. The further away I am from the charge's center, so we're counting from the center here, moving that, then we'll have the square of the amount changing there. So it's basically like the inverse square law all over again when we first talked about the intensity of sound and the intensity of light, but this time we're talking about it in terms of the electric field strength. If I actually graph that out, I can see that we can form a particular isotope shape here. So we can see on the charts, so here we have two types of electric fields. Obviously all this is showing is the electric field going in the two opposite directions. But what you can sort of see here is if we imagine our radius is 0, so imagine our radius point is 0 here, and this is our infinity points. And remember, the electric field can be sort of positive or negative depending on where you're looking at the field. So what we can see here, according to this equation, if the radius in which we're measuring this, r, is going to 0, then the electric field strength, you can see, gets exponentially higher. So this bit here, we can see that it gets exponentially higher as we get closer to 0. And we can see that as the radius gets infinitely large, so we're going further and further away from the center of the particle, the electric field strength goes to virtually 0. So that's the relationship that we are seeing here. Okay, so the next question is, obviously we want to quickly address is what is K. Now K is a constant. So you'll find the value of K in your formula sheet as well. Another form that K undertakes is this form here. So 1 over 4 pi, and then you got this Greek letter called epsilon. Okay, epsilon there. What this basically tells us is you can think of this symbol as the resistance to the electric field generated. So every field, when it's generated, will also experience some kind of resistance opposing it from moving in all directions. Okay, so resistance to it propagating in all directions. And this is a constant value, so this is a fixed number that's also found on your periodic table. The symbol we actually use is epsilon naught, and so epsilon naught, same idea here, but the naught actually refers to the resistance of generating an electric field in a vacuum. So resistance of electric field in a vacuum. And the reason why we generally use the vacuum as the reference is because that's where we expect to have the lowest resistance. So if we know where the lowest resistance point is, then we can work the other way around to find the overall strength of the electric field generated by a charged particle. Okay, so let's quickly calculate and see what the magnitude and direction of our electric field is here. So we have a positive charge, substitute our number in, so the K constant is 9.0 10 to the power 9 times the charge, which is 2 times 10 to the minus 5 coulombs, divided by 30 centimeters, which needs to be converted into meters. Okay, and so I'll leave that working out there. I'll come to this question first and then we'll go through the answers. Question 2, it says calculate the electric field due to a proton. So we're looking at E, trying to find what E is, at a distance of 8 there. So 8 is the separation we have. This is the average orbital radius, so we're looking at orbital radius, so R is what we're going to use. This distance is 4 orders of the magnitude larger than the size of the proton, which is about 10 to the power minus 15. So we can treat the proton as a point charge. Okay, so we are using the exact same idea. Okay, so we have the electric field strength, we have the K constant, the charge of a proton is the same as an electron. It's actually 1.062 10 to the power minus 19 positive to represent that the proton generates the field in that particular direction. The next one is the overall distance. So the average orbital radius of an electron in the hydrogen atom is that particular value there. Okay. And this distance, and then the distance of the electron orbit is 4 orders bigger than the size of the proton. So size of the proton is this value here. Okay, so that's sort of a giveaway here. That's more like a red herring. The value we're using is this one here, because we want to know what the strength of the proton's electric field is at this particular distance. So 8 minus 11, and then don't forget the square. Okay, so let's get the answers. Okay, so the answer for question 1 is about 2 to the power of minus, or to the power of 10, or 10 to the power of 6 in coulombs. Okay, so we have a pretty strong electric field strength there. And then our next one we have here, the electric field strength is 2.25 10 to the power of 11 Newton coulombs. Okay, so that's how you do the 2 questions there. Alright, the next one we have is Coulomb's law. So it is, in this equation, it's showing the interaction of, let's say, we'll call it charge 1, and the interaction of charge 2. And the question is saying, analyze and model for that interaction between these charges. So you can imagine we have 2 charges. One is, negative. One is positive. If we have different charges, they are going to attract. Okay, and what we know from this formula, as you can see here, if we assume that the charges are constant, then we can sort of say that the force experienced by the 2 charges is inversely proportional to the radius square. Okay. Again, it means that as r is approaching to 0, the force is approaching to infinity. If you actually look at the animation I have up here, you can see as the object goes closer together, the force sort of increases by an exponential amount, as you can see through the arrows there. So this is what we mean by Coulomb's law. Another thing you might also see is the magnitude of the 2 charges are the same. Okay, regardless of how massive they are and regardless of the type of charge they have. Okay, so Coulomb's law is basically stated as the force between 2 charges at rest is directly proportional to the product of the magnitudes of the charges. So, what charge the 2 particles have, inversely proportional to the square of the distance. So that's what we have there. Another way of rewriting this is we can say that the force is directly proportional to Q1, Q2, but it is inversely proportional to R squared. But at this point here, there were no units. Okay, so when Coulomb made this original law, we didn't have any units to measure charge. It wasn't until much later when we actually worked out what charge is through our understanding of current, and obviously, as you know now, we measure things, charges in terms of coulombs. Okay, so when we finally established the unit to measure charge, we could come up with a proper equation to express Coulomb's law. In this case, we add in a K constant for proportionality. So this formula is saying that the force exerted onto 2 charged particles is through this equation here. The K constant represents the ability of the medium to produce an electric field. So how well can the medium resist setbacks from the electric field So this is the equation we have here. One of the things I want to touch up on is, regardless of how big or small the charges are, the two charges will still experience the same force. Okay, so this is an important thing to take into account. So I could have a proton that has a charge of +4. I could have an electron with a charge of +8, even though -8, sorry, even though the -8 electron will have more electric field lines, so it'll be doubly dense. The positive charge will still experience the same force as the -8 charge. Okay, and we already talked about what the K constant stands for. We call it the permittivity of free space, so how well can an electric field be generated in a vacuum. Okay, so that's the equation we are dealing with here. Remember, it's key to point out the units. Force is newtons, charges is coulombs, distance always in meters. This is the formula that will appear on your data sheet, and this epsilon naught is also on data sheet. So keep that in mind. If you're not sure where it is, make sure you bring out the formula sheet to help you with your calculations. Okay, again, the equation will basically tell us the force of attraction or repulsion will get infinitely larger the closer the two charges are to each other, and also it will get smaller when you change the distance in separation, vice versa. Okay, so let's try and do some calculations. Now what you have here is nano coulombs. So nano is actually 10 to the power of -9 coulombs. Remember, when we're dealing with charged particles, they tend to be very small, and that's why they're never 1 coulomb. 1 coulomb is an incredibly large value. This one we have here, this is called mu, and you can imagine it's 10 to the -6. So mu, you can think of it, I don't know, like the Pokemon Mew, I guess. You'd sort of pronounce it like the same. It's not spelt the same, but that's the idea there. So you have two small spheres, A and B. We know that A is a +3 microcoulomb charge, and B is a -45 nanocoulomb charge. So we want to calculate the force between the two. So F is equal to 1/4 pi epsilon, which is 8.8 power 12 times the charge, 3 times 10 to the power -6 times 45 times power to -9. Okay, and also the radius of separation, which is 10 centimeters, convert that into meters, square. Okay, so I'll leave the answer in a second. I'll just do the working out for the next one. We have two positive charges that have equal charges, separated by that distance. Calculate the charge on each point charge. Okay, so we have a repulsive force of 6.48 nanonewtons or millinewtons. So the fact that we have a repulsion would suggest that the charges are either two negative pairs or two positive pairs. Okay, so let's just substitute that into our equation. Milli is 10 to the -3. Our K constant given to us here, so just substitute that in. Because we're dealing with the same charge, so Q1 and Q2 are the same, then let's just combine them together and call this Q squared. And the distance of separation is given by this value here. Okay, so Q squared is equal to 6.48 10 to the power minus 3 times 1.25 10 to the power minus 2 divided by 9 times 10 to the power 9. Square that and you will find, or square root that, and you'll find the individual charge value. Okay, so the value we get for number 3 is minus 0.121 newtons. This is an attractive force. The reason why it's an attractive force is this negative. Alright, remember when we first talked about vectors, negative implies that the charges are moving in opposite directions. Move in opposite directions. And just to help you sort of picture it, if I have two charged particles, so say a positive and a negative, and they're moving towards each other, you can see the arrows that I draw, they're both moving in the opposite direction to each other. So if it is negative, that's expected if we're seeing an attraction. You can see here in question 4, the force is positive, which means they're both moving in the same direction. So let's say we have, a positive charge, a negative charge, or positive charge as well. Then obviously we see a force of repulsion there. The charge we actually get for this is 1.06 10 to the power minus 8 coulombs. Okay, I think this is the last set of questions we have for Coulomb's law. It says the force between two identical charges, P and Q, is this value here. If the charges are that far apart, what is their magnitude? So what's again, it's also asking for charge. So we have 9 times 10 to the minus 5 equals to 9 times 10 to the power 7. Okay. Q squared, 2 millimeters, which is 10 to the minus 3 meters. So substitute everything across. We get that this is the square root. 9 times 10 to the minus 5 times so. Okay, so we can look at the charge there. And based on your answer above, are the charges positive or negative? Explain your answer. Well, we don't actually need to work out the charge. We already see the force here, and it also says it's repulsion. Okay, so the force is a repulsion, it's positive, so our force value is positive. This implies that the two charged particles are the same as each other, which means that it can be both two two positive charges or two negative charge pairs together, because that's essentially what we know. If it's the same charge, they're going to repel, and both cases are likely. Okay, so the value we have here is 2 times 10 to the power minus 5 coulombs. Alright, so that kind of concludes everything you need to know about electrostatic forces, Coulomb's law. What you can gauge from here is that we've already worked out the force exerted by an electric field on a charge. Today we also looked at a charged particle accelerating in a uniform electric field, and we also looked at Coulomb's law here. And the important takeaway with Coulomb's law is, regardless of the charge of the particle, both charges will experience the same force. So both charges experience the same force, regardless of any differences in the charge of the particles. Remember, like charges will repel, opposite charges will always attract. And that concludes our very first part of this content. The next lesson we are going to look at a concept called electric potential and equipotential points of electric fields. So stay in tune for that. Anyhow, thank you for watching this video. If there's anything you didn't understand, by all means re-watch it and see what new solutions you can come up with. Until next time, thank you for joining into the classroom, and see you later.